the first lecture is to talk about capacitors and inductors, and then the bit that you've actually got online is about how we analyse circuits with capacitors and inductors in them. So anyway, here's our plan for today. I wanted to start though by saying here was the circuit I put up in the first lecture, and we sort of said by the end of the subject you'll be able to analyse this. We're not quite there yet. We've certainly spoken about op-amps and resistors, and you can do the nodal analysis and work out the various configurations of op-amps, but we need to say a little bit more about capacitors to understand this properly. I know you put capacitors in your op-amp circuits. You looked at them there briefly, but now we've got to look at capacitors more seriously this week. And then when we do phasor analysis in the next week, you'll be able to totally characterise what that particular circuit is doing. Capacitors and inductors will give us something that resistors don't give us. Otherwise, we wouldn't need them. What they both give us is frequency-dependent behaviour. A behaviour that somehow changes with the input frequency. So if I have a fast sinusoid input, say at 10 megahertz versus 100 kilohertz sinusoid, the circuit will behave very differently. With just resistors, I can't get that. The behaviour is just V equals I times R. It doesn't matter what the input looks like. But with capacitors and inductors, it does. There's a frequency-dependent behaviour. It allows us to do things like build filters. So let's suppose this is the frequency spectrum along that axis, and we might have FM, different radio stations. So let's suppose one's jumping up there, one there, and one there. So this is across frequency, and the set of frequency there might be what you tune to. So this could be what? What's your favourite radio station? Don't listen to the radio. Does anyone listen to the radio anymore? What's your favourite station? Triple J. Okay, so here's Triple J. The order of the frequencies isn't probably right. It's what, 107.5 or something? Kilohertz. So megahertz or whatever. So that's sitting there. That's what this frequency means, and it occupies a band around that centre frequency that you tune into. My favourite, you all know that, Gold FM. All the classics from the 80s, 80s and 80s. Right down there, perfect for me. And another one, I don't know anymore. Is there still one called Triple M? There we go, Triple M. So there are your three radio stations. You want to get rid of everything except Gold FM. And so the first thing a receiver does, you have to build something that gets rid of these frequencies, passes these ones, and gets rid of those ones. So how do I build something that responds like that? Gets rid of Triple J and Triple M, just leaves Gold FM to listen to with no leakage from the nearby stations. That's a filter. It's a bandpass filter, and you couldn't build that just with resistors and op-amps and supplies. We need capacitors and inductors, and as soon as we've got those elements, we can make something behave this way, that at lower frequencies than we want, we can get rid of the signal, we can reduce the voltage if you like, and at higher frequencies than we want, we can make the voltage gain drop off. But in the middle, bang, we've tuned it to that particular frequency. How do we use inductors and capacitors to do that? Fundamental part of any radio receiver is this tuner, and inductors and capacitors play a critical role. So we want to learn about capacitors and inductors, what is their relationship between voltage and current, and then we'll look at things called first order circuits where we have a resistor and a capacitor, or a resistor and inductor. It's not all DC now. Things change with time. And so it will turn out we have to solve differential equations if we want to analyse circuits with capacitors and inductors. So we're going to introduce capacitance and inductance. They can be useful and or annoying. We will just consider the electrical properties, not the physics. And we'll see what we mean by annoying in a minute. They are all capacitors of different sizes and shapes. Maybe I'll drop off a little bit. So there are a bunch of different capacitors. You've probably already used some in the labs for different things, probably of the smaller variety. But all of those sorts of things, if you crack a circuit open, you see those tank-like things. They are tanks. They're storing charge. So a capacitor stores charge. You can use it for smoothing. They can clean noisy signals by filtering noise. DC blocking, just letting AC components through. Because they store charge, this thing that actually stores charge on some plates, it's like a short-term battery, if you like, a little bit like a battery. It can store energy for you and then release it later on. Filtering, they can be tuned to filter or pass certain signal frequencies, as I've mentioned, and timing, rough timing circuits for CPUs or microcontrollers. Capacitors, any useful circuit will basically have capacitors in it. And there's a blocking capacitor. If you make a capacitor big enough, it can be used as a short-term battery. And indeed, the Route 11 bus in Shanghai is powered by supercapacitors. Not big batteries, but by supercapacitors. It can restore up to 40% of their own electricity through regenerative braking, and it recharges at bus stops. So the difference here is you can probably only go a few miles on the charge on your supercapacitor. So they can charge them up. You can only go a few miles, and you've got to recharge. So that's not very good for a passenger vehicle, for your car. But the thing is, with capacitors, they don't hold their charge. You can't hold that much charge on them, that much energy, but you can charge them and discharge them very quickly. So quite a different profile to a big battery. Might be a long charge time, and you can, drive a long way. Here, quick charge time, you can't drive very far. Perfect for things like buses. It stops regularly at bus stops anyway. Okay, so you stop at a bus stop, you charge, and then you can drive along to the next bus stop. So there it is there, Route 11 bus in Shanghai, charging at the bus stops. All the charge sitting in under the seats, all this big supercapacitor storing all the charge. As it discharges, you can drive, charge at the next station. 10% of the energy costs of a diesel bus. This system here. Anyone been on Route 11? No, haven't been on Route 11. Gee. It should be in the list of things to do when you go and visit Shanghai. Get on. But yeah, only 10% of the energy usage. So that's a pretty good result. You may know, you saw some ads a while ago, but Mazda has developed a capacitor-based system to recover energy from regenerative braking or vehicle deceleration. You waste a lot of, you can build up all this momentum, all this energy. When you brake, you waste it. But if you can try and recoup some of that and store it, that's what this system does. Stores it in capacitors, and you can then reuse that energy for your climate control and other things for your vehicle and get some efficiency out of that. And you can boost the fuel economy by as much as 10% in Mazda's testing. So there's some supercapacitors. There's another supercapacitor. Anyone know that capacitor? Back to the Future, the famous flux capacitor, an important part of the time-travelling vehicle in Back to the Future. Capacitors are devices. What are they? Well, they have two conducting plates separated by something that doesn't conduct. Okay, so it keeps the charge separated. That's called the dielectric. So two conducting surfaces separated by a non-conducting dielectric. And there are tons of different types, all sorts of different dielectrics, the thing that doesn't conduct in between the plates. So the blue thing there would be the plate that has the charge sitting on it. The green thing's the dielectric. that doesn't let charge go through. So you can charge these things up, charge just sits there, basically doesn't leak away. Later on when you reconnect the circuit up, that charge can flow and cause things to happen. So they store energy in the charge that's built and separated on those plates. If you had to build a capacitor, that's how you could go about building it. So you might build a capacitor because you want capacitance to play a role in a circuit, but there are also situations where it's just there, even if you didn't necessarily want it there. So capacitance exists, for example, if you're building a printed circuit board and you're operating at high frequencies, they have this stray capacitance or parasitic capacitance, and it exists between tracks. So these are your wires on a PCB. You etch some conducting material on them, and if they're running side by side, it's a little bit like conducting plates separated by something. So that induces capacitance at high frequencies, and you have to take that into account when you're doing circuit design. And the smaller and smaller you want to get, the more important some of these effects can become. So stray capacitance can develop, and then you have to deal with it. You didn't intentionally put it in there, but you have to deal with it. So that's great, but voltage, current, V equals IR, what's the equivalent of Ohm's law for a capacitor? Well, it's essentially this, that Q equals C times V. It's almost the definition of the capacitance C. How much charge can you hold for a given voltage? Q divided by V is the capacitance. So bigger capacitors can hold more charge for the same voltage across the plates. If you can hold 10 coulombs of charge for a 1 volt across the plates, and it only builds up 1 volt across the plates, then you've got a 10 farad capacitor, as it's turned out. So capacitance is measured in farads, and C equals, if you like, Q on V. The total charge that's stored there divided by the voltage between them. The bigger the capacitance, the more charge you can store. C is the capacitance measured in farads, named after Michael Faraday, great physicist. We're more interested in current typically, so I take the derivative of Q with respect to T to get I, dQ dt, which must be C times dV by dt. That's the really key equation today. I equals C times the rate of change of voltage. All of a sudden, the rate of change is introduced. And you can see now why we start to get frequency-dependent behaviour. If the voltage is changing quickly or the voltage is changing slowly, it's going to change the impact of the capacitor. That's where we get our frequency-dependent behaviour from. So I equals C dV dt, very different. You might start to think about now, if we did Kirchhoff's voltage law around circuits with capacitors, we're going to have derivatives in play. That's why we end up with differential equations rather than just linear algebraic equations. Okay? Derivatives of voltage and current start coming in to play. So we can answer our first little question, which is just making use of I equals C times dV by dt. And I'll remind you of that because I haven't provided you with the notes. Remember that I equals C times the rate of change of voltage. If this was the voltage changing with time, given here, what is the current? And we're told C is 5 microfarads. So you know C, you're given a voltage waveform, you just need to calculate the derivative of voltage with respect to time and plug it in there, and you can work out the current. So the MELTS question is between 0 and 6, just that first bit. It's a straight line, so the derivative's nice and easy to work out. What is the current that's flowing? I think it should be posed on MELTS. So have a think about it. Just have to get your units right. Check your units, just from a quick look at the results so far. Microfarads, milliseconds. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and lock it there. So 50 out of 72 people said C, 20 milliamps. I do apologise, I know not everyone has the phone to access, so now I'll start putting up the options on the slides as well as on melts, so that if you're not accessing the melt system, you can still see the responses. That came up in some feedback on melts, so I'm sorry I wasn't doing that before. C is the correct answer, 20 milliamps. What is dV/dt for T bigger than 0 and less than 6? The rate of change of voltage with respect to time must be 24 volts divided by 6 milliseconds, which is 4 kilovolts per second. Just this straight line here, the slope is 24 divided by 6 milliseconds. But that isn't it. Remember, I need to multiply that by C. So I will equal 5 microfarads by 4 by 10 to the 3 amps, which is 20 milliamps. So it's 20 milliamps there. For T between 6 and 8, (6 milliseconds and 8 milliseconds), I've again dropped 24, but now I do it in 2 seconds. So very quickly, what's the current going to be? Negative 60. The slope's going to be 3 times the magnitude and negative, because now I dropped the same voltage in only 2 milliseconds instead of 6. So it's going to be minus 60 milliseconds. You can save a bit of time, or you can redo the calculation. And what about after 8? Sorry, milliamps, thank you very much. What about in this period of time? What's the rate of change of voltage with respect to time? 0. So the current is 0. So you could quickly plot here, if this was time in milliseconds, if this was current in milliamps, I'd start at 20 until I got to 6. At that point, I go down here to minus 60. I don't stay there for that long, actually. And then I'm back up to 0. So I go from 20 up to 6, drop to minus 60 milliamps, and then up to 0. So that is just using this I equals C times the time rate of change of voltage and applying that. And about 70% of you were able to do that. So if I equals C times the V by dt, how could you write the voltage? Well, you have to integrate the current. Fundamental theorem of calculus relating, if I is the derivative of voltage with respect to time, then V is going to be the integral of current. And that's all this slide says. If you know the voltage at some time t0, you add that to 1 on C times the integral between t0 and t of I t dt. That's charge building up on the capacitor. Right? As current's flowing into the plates, charge builds up. That's what happens. We fill the capacitor, the charge builds up, the voltage increases. If the current flows in the negative direction, the charge is decreasing on the capacitor plates. So you integrate the current waveform to get the voltage that is stored on the plates. Really the fundamental theorem of calculus. Something else we're interested in. Capacitors store energy in charge. Well, if I know the voltage on the plates, how much energy is stored there? Turns out it's a half CV squared. How do you get it? We remember that P equals V times I, the voltage across the plates times the current through it. I substitute in for I for a capacitor, C times the V by dt. So that's the power being absorbed instantaneously at time t. To get the energy stored, I have to integrate the power. So I do that. This integral of V times dV by dt is like integrating V dV, a half V squared comes out of it. And so that's why I have the half V squared there. So a little bit of calculus, but the energy stored, if I've got voltage V on the plates, there's a certain charge there, there's energy stored there. It's a half the capacitance times the voltage squared. Now remember, for resistors, what was it? Voltage V across a resistor, not storing any energy, but the power was V squared on R. Doesn't store any energy in a resistor instantaneously, but capacitors can. They can actually store energy. Gotta love that one. Honey, I'm home. Beautiful. Here are the 4 things we've seen about capacitors. 1, C equals Q divided by V. Big capacitors can store a lot of charge for the same voltage across the plates. Nice way to think about it. The more charge for the same voltage, the bigger the capacitance. Probably the most important one for us. I equals C times dV by dt. That's like Ohm's law for capacitors for us. You can integrate the current to get the voltage, and the energy stored, we've just seen, is a half C times V squared. That's really everything we need to know to characterise capacitors. Like with most things, you can blow them up. So I'll have a little bit of a rest break while we watch some people blowing up some capacitors. Always good fun. Don't do this in your lab test this week if you want to pass. I think this is slow motion. There it is, smoking. You've just blown it up. You can see what happens. All of these components have ratings. They have ratings, and if you exceed them, you can certainly blow them up. Resistors, capacitors, inductors, they all have limitations. What are they? What are they? They don't look like capacitors, and this lecture's on capacitors and inductors. I think they're inductors. So your classic capacitor, you think these conducting plates separated, inductors, coils of wire. Think coils of wire, because that's essentially what all of these are. Coils of wire, different number, different diameters, different number of turns. That all determines different inductances, but they're all examples of inductors. Inductors are essentially coils of wire, sometimes wrapped around a ferrous core, though not always. Two inductors wrapped around the same core actually form something called a transformer. They're all over the place, changing voltage levels around in our power distribution system. Like capacitance, all circuits have inductance, particularly long lengths of wire or long PCB traces. So it is everywhere. Sometimes you don't want it there and you have to deal with it. But very often, inductors are, we'll be looking at them as a useful part of a circuit. When you try to change the current through a coil, things happen. Voltages get induced. And so that's what leads to the basic equation for an inductor. Ohm's law, if you like, for inductors is now V equals L times the rate of change of current. So given a certain inductor, if I really try to change the current through it quickly, the voltage builds up on that inductor. Okay? Or it takes a lot of voltage to change the current through an inductor quickly. Is another way to think about it. A lot of voltage would have to be applied to the terminals of the inductor if I wanted to change the current through it quickly, because there is a resistance to that change. So L is the inductance, and it's measured in one of the best named units you've ever heard, the Henry. So inductance is measured in henries, using the same things that we did for the capacitor. If V is the time rate of change of current, then the current will be the integral of the voltage. We're going to have to integrate voltage if we want to look at the current. And the energy stored. When there's a current I through an inductor, there's an energy stored there in a magnetic field, a half Li squared. So the roles of I and V, voltage and current, switch around compared to the capacitor. One stores energy in an electric field. The capacitor, an inductor, stores energy in the magnetic field. And there are the units, the Henry, the millihenry, and the microhenry. As I said, got to be one of the best units you've ever heard of. We don't have to work, we sort of know all we need to analyse certain circuits with capacitors and inductors, and that's when nothing's changing. What we call DC steady state. If no voltage or current in a circuit is changing, it's sitting there, it's got capacitors and inductors in it, but no voltage or current is changing, well, what happens to capacitors and inductors? Well, a capacitor, I equals C times the rate of change of voltage. There is no rate of change of voltage, so I equals 0. At DC, the capacitor is an open circuit. I equals 0. So if you wanted to replace the capacitor by something or understand how it behaves in DC steady state when nothing's changing, well, it's I equals 0. It's an open circuit. No current will flow through that capacitor. An inductor, on the other hand, must be V equals 0, because the rate of change of current would be 0 if nothing's changing. V equals 0 is a short circuit. So you can see how capacitors and inductors, and let's think about it. Why would an inductor be a short circuit? Well, it's just a piece of wire, happens to be wrapped around in a coil type shape, But once everything's settled down, it's a piece of wire. So it's a short circuit to DC. A capacitor, two plates with something that doesn't conduct in between, it's an open circuit to DC. That means we can tackle a question like this. Find the total energy stored in this circuit, assuming everything has reached steady state. So it's been like that for a long time. There are capacitors and inductors in there, but we know we can get rid of them. The two inductors become short circuits. So this just becomes nothing. Short circuit, and these become open circuits. So I can get rid of that. The circuit I need to then analyse is that one. There aren't any inductors and capacitors in it. There are short circuits and open circuits where they were. But if I want to find the energy stored in the circuit, I need to find what about the inductor? The current. Remember, a half Li squared, there's a current flowing through an inductor in DC steady state. What is it? And a half Li squared will be the energy stored in it. So although they're not there, the IL1 is, because I've got to find that current up the top there. Because if I back up a little bit, that was the current through this inductor, IL1. And notice that the direction doesn't matter. It doesn't matter whether it's this way or this way. The energy stored doesn't care about that. It's a half Li squared. So the sign doesn't matter. IL2, that's where the other inductor was. This is where the first capacitor was, and this is where the second. I need to find the voltage on the capacitors and the current through the inductors, and I can find the total energy stored in the circuit. So the melts question is, if I have to analyse, and I need to find IL1, IL2, VC1 and VC2. Let's see if we can find VA, the voltage at that node up there, VA. And here are the different possibilities. What is the voltage at node A? You could do Kirchhoff's current law at that node. It's a nodal analysis where one of the nodes up here you already know is sitting there at 9 volts. I'll just post that. And unlock it. So again, I hope you can make that separation. Once I've got the circuit in that form, it's not really about capacitors and inductors, it's can you do Kirchhoff's current law at a node. Once you've got the IL1, the IL2, the VC1 and the VC2, can we use some stuff about capacitors and inductors to calculate the stored energy? You don't have to worry about IL1, IL2, VC1, VC2 yet. Just what is VA? Voltage at node A. You should only need one equation. Feel free to chat, discuss. Wait till we get 50 responses. So maybe that's Kirchhoff's current law at that top, at node A. All right, a few more. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, perfect. 60 responses. 48 out of 60 said A, 16.2 volts. Which is correct. So, hopefully everyone can see how I got that. The first one is this current here. VA minus 9, that's stuck at 9 volts, that node there, divided by the resistance 6. That's the current that way. The current that way is just VA, goes through 3 and 6 to ground. Haven't put ground on there, so that's a bit sloppy. Ground. VA on 3 plus 6 is VA on 9. And minus 3 equals 0. Multiply through by 18, or do whatever you want to solve it, and you'll get that VA is 16.2 volts. VA is 16.2 volts, and most of you were able to get that. So if VA is 16.2 volts, we have to find IL1. What's IL1 then? Well, if I know VA, and I know that's at 9 volts, I reckon IL1 is 9 minus VA divided by 6. 9 minus VA divided by 6, which will be minus 1.2 amps. IL2, this current here, will be VA divided by 9, which is 1.8 amps. Okay, so once I've got VA again, like it's once I've got the node voltages, you can find the other voltages and currents. So IL2, this current here, will be VA divided by 9. What's VC1? The voltage on capacitor 1. This thing here, what is it? VA. It is VA. It equals VA, which is 16.2 volts. What about VC2? This voltage here. 6 times IL2. 6 ohms times IL2, which will equal 10.8 volts. So classic circuit analysis, find the node voltages. All the other currents and voltages are relatively easy to find. I've got my currents through my inductors. I know the voltage sitting across the capacitor plates in steady state. And so to finish it off, the energy stored in this circuit will be a half L1 IL1 squared plus a half L2 IL2 squared plus a half C1 VC1 squared plus a half C2 VC2 squared. All of these components storing energy. Plug in your values for IL1, IL2, etc., and the inductor and capacitor values, and you should get 13.46 millijoules sitting there stored in that circuit. Okay. So the idea there, at DC steady state, direct current, meaning that all of the sources are just direct current things, 6 milliamps current sources or 12 volt voltage sources. At DC steady state, circuits with capacitors and inductors don't really hold anything new for you. Inductors short circuit, capacitors open circuit, you just analyse normally. You might be interested in finding currents through inductors, voltages on capacitor plates, because it tells you about the energy stored. Now, what about two capacitors in parallel or two capacitors in series? Think about this. Would you expect capacitors in series or the same capacitors in parallel to be a bigger capacitance? Think about the definition of capacitance, Q on V. So for the same voltage across the plates, the more charge you can hold, the bigger your capacitance. Would you expect capacitors in series or capacitors in parallel to be bigger? Who thinks parallel to be bigger? That's the opposite of resistors. But it shouldn't be counterintuitive. If I've got a whole lot of capacitors in parallel, I can have a certain voltage. Every one of them can hold charge. So I keep putting more and more in parallel and I'm holding more and more charge. So the equivalent capacitance must be getting bigger, not smaller like resistors. Indeed, that's the case. So, there's resistance, inductance, and capacitance. You'll never forget them. Series capacitors, the capacitance gets smaller. If I put a whole lot of capacitors in series, it's like parallel resistors. Why? Well, because if there's a certain charge stored, I could have Q stored there, minus Q there, Q there, minus Q, Q there, minus Q. It doesn't help me store any more charge, and the voltages all add up. So in other words, the voltage drop is getting bigger, but the charge stored is not. So that's a smaller capacitance overall. Whereas what we were saying about the parallel ones, this could store Q, minus Q, Q, minus Q, 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 etc. But the voltage is just the voltage. It didn't get any bigger. So, and I'm storing 4Q there, so the capacitance should be 4 times as big, if you like. So, parallel capacitors are like series resistors. Series capacitors are like parallel resistors in terms of how they add. Now, you should be able to prove that. All you know about capacitors really is I equals C times the V by dt. So if we said, prove that the equivalent capacitance of a series combination is blah, 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 how would you do it? Well, I can write V is V1 plus V2 plus dot, dot, dot plus Vn. Therefore, the time rate of change of V with respect to t is dV1 dt plus dV2 dt plus dot, dot, dot plus the derivative of Vn with respect to t. What's the rate of change of V1 with respect to t in terms of I? I on C1. I on C1. Isn't it? Because I equals C dV dt. And the current is I through that capacitor. What's dV2 dt? The time rate of change of voltage on that capacitor. I on C2. It's the same current through all of them. I on C2 plus dot, dot, dot plus I on Cn, which is 1 on C1 plus 1 on C2 plus 1 on Cn times I. So I've got dV dt overall is this times I. So that whole thing there must be 1 on the equivalent capacitance. How do you prove it? Well, you use what you know about it. Here we use Kirchhoff's voltage law with I equals C dV by dt, the fundamental VI relationship for a capacitor. So you could correspondingly prove that parallel capacitors must add up. Inductors, on the other hand, behave much like resistors. The more inductors you have, think about it. You've got a coil of wire, and then another coil, and then another coil. It's almost like you've just got more turns, more things, so the inductance is just getting bigger. Series inductors just get bigger, whereas parallel inductors, there are more paths for current to flow. So the inductance of a parallel combination is actually less, as you have it down there. So if you like, inductors are like resistors, capacitors are the other way around. But that should make intuitive sense. Not something you should have to remember, but from the intuition, the knowledge of what capacitance means, ability to store, how much charge can you store per volt across the plates, those things should make good intuitive sense. Thanks for coming in so early on a Monday morning, and see you on Wednesday.